Let's talk about double integration in polar coordinates. We already know how to do this in rectangular. Let's do a quick flashback. Consider double integral over region R, some function of two variables with respect to area. Now, of course, we have grown accustomed to doing this over a region described in an XY Cartesian coordinate system. And if we simply take a slice dx of width dx and we take a horizontal slice of width dy, we end up with a nice little rectangle, and that's a reminder of what dA is. But if we were to choose to go out farther and put dx here, if we left dy the same, we'd have the same little rectangle. And we could go up if we wanted to and slice dy up here, and we would still get a nice little rectangle. In other words, dA is not affected by its location in the coordinate system. On the other hand, let's talk about polar. If you have a polar coordinate system, you know that this is now the polar axis, which is traditionally identified with the x-axis, and we are measuring, in addition to r, which is the variable associated with the polar axis distance or radius, we also have theta, which is the angle measured counterclockwise. If we took a slice of angle and called it d theta, well, d theta would have a pair of rays coming out from the pole, and it gets wider as you go out further. Also, if you pick a dr, because remember, r is distance, so dr would be a little increment of distance, we would get, with dr and d theta, we would get a little wedge of area right there. So there's dA in polar coordinates. But now something funny happens. Suppose we head out and let's say we double the distance. We double the distance and we go out here instead. We leave dr the same. We leave d theta the same, but we've gone out farther, and this distance, having increased, results in increasing the area. In fact, if you double the distance, you effectively double that area. If you triple the distance, you would triple the area. It's directly proportional to its distance from the pole. dA is not equal to dr d theta. It's equal to r dr d theta, where r is providing the scaling factor that makes the measurement of how much bigger it is the farther out you go. Having taken that into account, we can now try to use it in an example for integration. But first, I'm going to do a problem that we knew how to do before, and I'm just going to use rectangular coordinates as a setup. And then we'll switch over and do it again in polar. So let's say we have a nice, perfectly round quarter circle. That's my region R. It's in the first quadrant, and y is the square root of 4 minus x squared. So it's of radius 2. So here's my quadrant, first quadrant region. And let's suppose I'd like to know the value of the integral over the region of x. Well, we know what that is. It's going to be the integral from 0 to 2, the integral from 0 to the square root of 4 minus x squared, x dy dx. When we partially integrate this, partially integrate x with respect to y holding x constant, we just get xy. So here's xy as y is evaluated from 0 up to 4 minus x squared. and we still have dx left over. Plug in and simplify just a little bit. We just get x square root 4 minus x squared dx. Plug in 0, you get nothing. Now this should look familiar to most of us. The derivative of what's inside is just minus 2x. And we have x out here, so we're missing a minus 2. So if we integrate this, there could be a detailed u sub setup if you wanted, but I'm going to shortcut it a little bit. We're missing a factor of negative 2. This is a 1/2 power. It's going to become a 3/2 power over 3/2 as x goes from 0 to 2. Okay? And when we plug in, let's see, the 2's cancel. I have minus 1/3. Plug in the 2, that gives me 0 to the 3/2. Minus a minus means plus 1/3. Plug in a 0, that's 4 to the 3/2. 4 to the 3/2 is just 8. The answer is 8/3. So there's one more example of a double integral in rectangular. Let's switch over now and look at this in terms of polar coordinates. The polar coordinates won't be too hard because, well, first of all, we still have that quarter circle region. And the quarter circle region in here, 2, that's on the polar axis. By the way, this is theta equals 0. And what we used to call the y-axis is theta equals pi over 2. Here's my region R. The description of the region is very nice in polar coordinates because theta is going from 0 to pi over 2 as R is going from 0 out to 2. All constant limits for our integration. And therefore, when we evaluate the integral of x with respect to area over R, we have 0 to pi over 2, 0 to 2. We know what x is. In polar coordinates, it's just r cosine theta. And don't forget, here's dA, r, dr, d theta. Thou shalt not forget the extra r. Presumably you could have d theta dr, but usually it's r dr d theta that we use as the preferred order of integration. If you simplify, just to make sure there are no mistakes, here's r, this is r squared. Cosine theta, dr, d theta. Integrate the r factor. Well, you know what that's going to do. That's going to give us r cubed over 3 from 0 to 2. I don't have to embellish these with r equals 0 and r equal 2 because there's only the one variable there. Cosine theta is left over, and we still have to integrate with respect to theta. This gives us 8/3. The antiderivative of cosine is sine from 0 to pi over 2. Plug in, that gives us 1 minus 0, so we just get 8/3. The result we got before. So that's encouraging. That's what we were hoping for. Now let's take a look at another property of integration with polar coordinates. This will give us a rather familiar looking result. Let's suppose you have some function that says r depends on theta. And you're going to go from theta equals alpha up to theta equals beta. And that's my region R. You may recall, you should recall, the area of R can be obtained by just double integrating 1 with respect to area. If we do this for that region, we go from alpha to beta. We go from 0, from the pole, out to that function, f of theta. And there's 1, and this is r, dr, d theta. So integrate r with respect to r, And we very naturally have 1/2 r squared from 0 to f of theta, and d theta is left over. By the way, when you plug this in, here's my alpha, here's my beta, I have 1/2 f of theta squared d theta. And reminder, this is the area of R. Have you seen this before? You should remember having seen this in Calculus 2 because it's the formula back in Chapter 10. The area is equal to 1/2 f of theta squared with respect to theta from alpha to beta. And if you have a region between two curves, then you have f of theta squared minus g of theta squared, the outer function and the inner function, and you end up with this f squared minus g squared formula, which is exactly what would have happened if we had had f and g bounding the inner and outer edges of the region R. So this just takes us back to something we knew already. Let me warn you about a tiny little problem, actually a rather significant problem, when it comes to integrating in polar. And so here's the warning. If you are asked to do something like finding the area, let's just talk about the top half, the top region that lies inside this cardioid, but outside the circle. And you'd think, well, I can just use f for my inner and square it, and g for my outer and square it, and subtract the two. But let's remember what these curves are. This is a circle of diameter 2 that's off-center. This is r equals 2 cosine theta. This is one of our old cardioid buddies. It's r equals 1 plus cosine theta. Plug in 0, you get 2. Plug in 0, you get 1 plus 1, you get 2. So this is where theta equals 0. No surprise to anyone. But check this out. As theta grows, cosine shrinks. And when does cosine reach 0? At pi over 2. So limits of integration for anything involving this circle would require 0 to pi over 2 if all you wanted was the top half. But this one, we start off at 2 when theta equals 0. And when you reach pi over 2 and cosine is 0, you're up here at 1. You don't get to the pole until theta equals pi. If you're going to work on a problem like this, my recommendation is do the top part and the bottom part separately and just subtract them. Because when you're doing integration in polar coordinates, you have to watch out for the limits of integration because they might not agree for different regions. And so now we've done some examples in polar, and I hope that's helpful.